Hello, this is Professor Hampi Holi, Professor of Mathematics, GIT Belagavi. We are meeting again for lecture number 2 for the topic sampling distribution and testing of hypothesis. This is basically for module 4 of KLS GIT Belagavi students, but may be useful for many other students also. For semester students, especially non-CSIS students, this module I am just taking. In the last module, we discussed a few important things: what is meant by population, what is meant by sampling, what is meant by hypothesis, and after those definitions, we took some examples also. Examples 1, 2, 3, 4, 5, and through examples we saw that given a sample, whether it belongs to the population or not. Like given it some 100 tubelites, whether it belongs to Crompton, whether it belongs to company XYZ or not, we can test using some statistic. Usually we are using only two statistic measurements here, that is, one is mean, one more is standard deviation, and sample size becomes important. We claimed that conventionally, if the sample size is up to 30, we take it as small sample. For small sample, there is a different type of approach, and we are dealing about big samples. For big samples, whatever the distribution Z statistic we take, that behaves as a normal distribution. This is because of there is a theorem known as central limit theorem. Because of that theorem, any large sample can be converted to a normal distribution sample using this conversion, which is this is known as shifting of origin. This division is scaling. By shifting of origin and scaling, this Z behaves as standard normal variate with mean 0 and standard deviation 1. Using that approach, we used this hypothesis as well as how to inference. So given an example, what all we do for the examination point of view is we take what is the sample size, what is sample average, the sample mean, what is standard deviation, and afterwards how to set a hypothesis and how to conclude whether the sample is rejected or whether using this last number, whether we reject or accept the hypothesis, and how to conclude. This is important. In every example, we did that. Now, with little deviation, in lecture number 2, I start with example 6. The mean and standard deviation of maximum loads supported by 60 cables are mean is 11.09, standard deviation is 0.73 tons. That is, what is the meaning of this? A company is manufacturing some 60 cables, maybe copper cables, maybe any cable, and there is a bearing capacity, that is on an average 11.09 tons should be bearing capacity with plus or minus 7.73 tolerance. It is 11.09 plus or minus 0.73, 11.09 minus 73, 11.09 plus 73, or in that interval 11.09 minus 73 to 11.09 minus 0.73. So given this information, average, standard deviation, and sample size, suppose you are taking a sample, suppose its average is about 61, average is about 12, or average is about, this is the average. If any other sample of 50 cables or 20 cables or suppose 60 cables only, if the average is 11.1, whether 90 with 95% confidence, whether I can tell that that belongs to this type of population only. I am repeating, please listen it very carefully. Suppose I am taking one more sample, and that sample has got average 11.1 or 11.2 with similar statistic 0.73. Whether with 99% confidence I can tell that it is of the same category of cables, or whether with 95% of the confidence. So what are the numbers plus or minus 11.09, so that I can claim that with 95% confidence I am sure that this is satisfying the criteria of loads. See, interestingly, if it is satisfying the criteria of loads of 99%, you are more sure that your product is more correct. Then you can give more guarantee, like 5 years guarantee you can give. You might have heard of many things that in a market, suppose a vehicle comes, then some of the companies tell that engine is guaranteed for 5 years, upper body is guaranteed for 2 years. It is because of this different type of confidence level. If we take a good Indian company, then it gives guarantee for suppose engine and less guarantee for body. If you go to a company which is manufactured by China, usually they give less guarantee for engine and more guarantee for the body, because somehow they want to manufacture cheaper and penetrate the market. And now the scenario is different, don't want to talk about it. Now coming back to this example, 11.09 plus or minus, what should be the criteria for 95% confidence that this 60 cables, these cables are satisfying this criteria of load bearing, and similarly 99% confidence limits. So we are going to find two intervals, one interval which is smaller, 95% confidence. For bigger, natural common sense tells that it should be bigger interval, 99% confidence. How do we find these two intervals? Let us see. So now given data, you just note down sample size 60, average 11.09, that is bearing capacity 11.09 tons and 0.73 tons with the standard deviation. For big samples, we take sample standard deviation, yes, and population standard deviations are same. For small sample, this becomes different. That when we come to small sample by name T distribution, we will demonstrate that how they are different. Now for 95% confidence limits, what all we have to do is, whatever the average X bar is given, for that minus 1.96 into sigma by root n, where sigma is this, n is 60, which is more than 30. And upper limit of the interval is plus sign here, that's all. So when I substitute these 11.09 and sigma as 0.73 and n as 60 here and here, I am going to get 11.09 minus one quantity and 11.09 plus quantity. That is around about 11.09. If the load bearing capacity that sample has got mean, any sample, if it falls in the average, that average of that sample falls between 10.91 to 11.27 tons. Once I am repeating, suppose I am taking one more sample of 60 cables, and the average bearing capacity of that, load bearing capacity of that falls, that X bar of that falls in this interval, with 95% confidence, I'll tell that that belongs to this company, that will satisfy this criteria, 95% confidence. For 99% confidence, instead of 1.96, this becomes 2.58, which is with other data same, X bar, sigma, root and same, which becomes 10.85 to 11.33. You can see that the width will be little bigger here. Bigger the width, you are more confident. If minus infinity to plus infinity is there, you are always 100% confident, but that doesn't make any sense. But if this mu is 11.09, leave 11.09 is, instead of that 10.85 to 11.33, which is bigger than this. If the sample mean falls in this interval, then we are 99% confidence. That's why this is known as confidence limits for 95%. These are the confidence limits for 99%. In examination, you'll be getting such things. What all you have to note down? N, X bar, sigma. For 95% confidence limits, you have to remember this part. Mu, you don't put anything, and X bar, sigma, root n, in both the upper and lower limits you substitute, you are going to get two real numbers, which is lower limit and upper limit of the confident interval of confidence we call. Similarly, for 99% confidence, instead of 1.96, this will be 2.58. So now we'll move to the next type of example. So by mistake, this is example 6. Again, example 6 is there. You can correct it as example 7 or whatever. So example number is not so important, of course. Here we go. A population consists of 4 numbers, 3, 7, 11, 15. Some 4 numbers are there. That is a population. Consider all possible samples of size 2 which can be drawn with replacement from population. Find the population means, the population standard deviation, sampling distribution from means. So through this example, what is the meaning of sampling distribution, I'll tell you, and means and standard deviation of that sampling distribution. Let us understand these 4 questions. Now, given sample, average of that given sample, population mean, just add and divide by 4. Standard deviation formula is there. Xi minus x bar square means what? 3 minus 9 whole square, 7 minus 9 whole square, 11 minus 9 whole square, 15 minus 9 whole square. Usual school standard deviation formula, divided by 4. So that sigma becomes 4.47. We found that population mean and population standard deviations are 1 and 2 are here only, 9 and 4.47. Now possible samples. Now I have to consider sample size of 2. You take any 2, you take 1, keep it here and replace it back with replacement. Replace it back and take any one thing randomly. So that all possible things are 2 samples, 3 3, 3 7, 3 11, 3 15. With 3 these are possible. Similarly with 7, 7 3, 7 7, 7 11, 7 15. From each one starting from 3 4, starting from 7 4, starting from 11 4, starting from 15 4 are possible. Totally 16. And average of these, each of these are samples. There are 16 samples totally. So now each of these have got average 3 plus 3 divided by 2. Each sample has got sample size 2. 3 plus 3 divided by 2. 3 plus 7 divided by 2. 3 plus 11 divided by 2. And so on up to 15 plus 15 divided by 2. Which is this, this becomes the variable. That is average of samples becomes the variable. So that 3 is occurring once. In this whole 16, 3 is occurring once. 5 is occurring 1, 2 times. 7 is occurring 1, 2, 3 times. Like that, frequency distribution is formed for this, all these statistics. That is, this becomes, given this sample, we created a sampling distribution with average as the variable of these samples. So average as the variable, if the frequency distribution is created, that becomes the sampling distribution. Now, its mean and standard deviation you have to find. That is the question number 3 and 4. Sampling distribution of means of sampling distribution of the means is found here. This is the sampling distribution of means. Answer to the question number 3. And fourth one is, what are the means and standard deviation of this distribution? Just like school knowledge, what are the means and standard deviation of this? What does it mean? Summation fi xi by summation fi, that is 3 into 1, 5 into 2, 7 into 3, 9 into 4, up to 13 into 2. You do it and add all those things, you will get summation fi xi by summation fi is 9. And afterwards use standard deviation formula and you will get standard deviation as square root of 10. So this is one more type of examples. Note down that. Now using these, all these examples, we saw that how to find, how to infer given a sample whether it belongs to the population or not. Now this is all for big samples. Now I am coming for small samples. For small samples, we have got what is known as, that is previous one is Z test. This is Z test we don't call, but I can just for the name's sake I am calling it as Z test. So this is T test, or student is the name of the mathematician, just like in India we have got name as Vidyarthi. So there will be name as student in foreign countries. Student T distribution. So the statistic here is x bar minus mu by sigma by root n. Sample size should be less than 30. And similarly, if there are 2 samples, this is the testing statistic, x1 bar minus x2 bar by all these things. So this degrees of freedom is one more new parameter here, which we will study in the, we shall see in the examples. So how do you do that? I am taking from second example. See, here the life of electrical bulbs becomes the variable. It is, suppose I am taking 10 bulbs. So 10 is less than 30, sample size is 10. So small size. So life in 1000 hours, that is into 1000, into 1000, into 1000 you have to make. That is, this into 1000 is 4200. This into 1000 is 4600, 4200, 4600 hours. 10 bulbs are tested and they will be lasting for first bulb 4200, second bulb 4600. So instead of that, talking in terms of, we'll talk in terms of 1000 hours. So each one is divided by 1000 and this statistic is created. Now, whether we can conclude that whether we can have the hypothesis that on an average the bulb lasts for 4000 hours. So there is a sample of 10 bulbs. This is the data given, which is actual the bulb is burning for so many hours. Okay, electric bulbs for a life of the bulb means so many hours they are burning. See, hours is there here. Whether we can conclude that on and average means this is the population mean. Conclusion means population mean. On and average 4000 hours. Targeted mean is population mean. But sample mean we have to actually calculate. So mu means this is the notation for sample population. Whole company is manufacturing so many bulbs. From that 10 bulbs are taken. So 10 is sample, but the company is targeting for on and average 4000 hours. But because of the human error, machine error, exactly 4000 hours the bulbs may not last. But on and average 4000 hours plus or minus like 4200 hours, some bulbs may last for more than 4000 hours. Suppose a TV tube should last for 2 years, some TV tubes may last for 4 years, some TV tubes may last for 1 month. So it depends on manufacturing error. But on an average, if the more number of bulbs are there around the average, we tell that it is more correct company. Now, population mean is 4000 hours. Test statistic t-test gives us. So we call it not statistics, please. It is statistic. So x bar minus mu by sigma by root n. So x bar is 4.4 means what? Add all these, divide by 10. S means x minus x bar square by n minus 1 square root of that. X minus x bar square means you know x bar 4.2 minus 4.4 whole square plus 4.6 minus 4.4 whole square plus 3.9 minus 4.4 whole square. And every time you have to take x from here till 5.6 minus 4.4 whole square. So that addition becomes 3.12 divided by n minus 1 means here 10 minus 1. So if there are 10 samples, it becomes 9 degrees of freedom, because if you know the sum of this, so if you know the sum of this, you can find, if you know the 9, you can find the 10th one. So if I know 9, it is enough. Once again, I'm telling, if I know 9 items and if I know the answer, sum of the all these terms, then if I know 9th also, I can find the 10th. Like that, if there are 10 items, 9 minus n 10 minus 1 means 9 degrees of freedom here. When I substitute x bar as 4.4, sigma calculated that 0.59 and square root of 10, which is 2.123. Now, whether this 2.123 is how to test which term to be compared. For 95% confidence, we have got one more table known as T distribution table. At 95% confidence means 0.05 level of significance. Both mean same. For 9 degrees of freedom, because there are 10 samples, 10 minus 1 means 9 degrees of freedom. How this 2.26 comes, let us see. See, this is the T distribution table. This is 9 degrees of freedom this is degrees of freedom 9. For this 2.26 is here. For 95% confidence limits means 0.05 level of significance. So this 2.26 has come because of 9 degrees of freedom and 95% confidence. Suppose there is 13 degrees of freedom and you want 99% confidence. What is the number? 13 degrees of freedom, 99% confidence. 13 degrees of freedom, 99 means 0.01 significance. 13 degrees of freedom, 99% confidence means 3.01. One more. Suppose 95% confidence, 11 degrees of freedom, 95% confidence, 11 degrees of freedom. So that is intersection of these two lines. One line, second line, 2.20 is the number. So now 9 degrees of freedom, 95% confidence, 2.26. We'll go back to that example. So that T statistic, you have to compare whatever you have calculated. You have to compare to that number as whether that number is less than 2.26 or not. So we got 2.123. If that number is less than 2.26, which is from table, in examinations you will be given the table or directly you may be given this data. So you have to compare. If this is less than this, then whatever the hypothesis is there, it is accepted. If it is something like 3.1, 3.6 or 2.27 also, which is more than 3.1 is more than 2.26. If this is 3.1, then it will be rejected because 3.1 will be more than 2.26. Now t calculated is less than t table value. That's why we conclude that our hypothesis is accepted. Conclusion: we accept the hypothesis that average lifetime of the bulbs of this company is 4,000 hours. So what we had assumed, there is no significant difference between the whatever the sample is there and the population is there. That is, instead of this, you can tell that average life is 4,000 hours. Both are same. And because of this conclusion that just like chemistry test, here we are going to test something because of sample testing, 2.123 is less than 2.26. This is a test. More than is rejected. More than this rejected, less than this any number, less than this it is accepted. Hence accepted means 4,000 hours is the on and average life of the bulb. Next example, a group of boys and girls. Here two groups are there. We are given intelligence test. So how many boys? 12 boys, less than 30. How many girls? 10 girls, less than 30. So both are small samples. A group of boys and girls were given intelligence test. The mean score of boys is 74. The mean score of girls is 70. So with a standard deviation of 8 and 10 respectively. See, this is the hypothesis. In the question only the hypothesis will be there. See, in examination, given data you have to write the proper hypothesis and find a statistic and conclude. For framing hypothesis also there will be marks. First frame the hypothesis, write the data properly. And in the previous example what we did, so here also, see in the previous examples what we did, I will show you once again. First you have to write the hypothesis. Okay, here I am going. First you have to write the data, hypothesis, find statistic, that is Z value, conclusion, then final here acceptance or rejections, here conclusion. Once again, data given, hypothesis, find the calculated value of Z, compare it, reject or accept, final conclusion. All these steps have to be done. Coming back to our examples of boys and girls now, which is a T distribution we are doing. This was the example. A group of boys and girls were given intelligence test. The mean score and standard deviations are given. So mean 74 for boys, 70 for girls. Standard deviation 8 for boys, 10 for girls. And sample size 12 for boys, 10 for girls. To be noted, sample size need not be equal for comparison. For any research also, sample size need not be equal. That is very much important to be noted. So how do we start in the solution? Given data. For first data, N1, X1, S1. N1 sample size, X1 bar mean 74. S1 is sample standard deviation. Similarly, N2 10, X2 70, and S2 10. So here hypothesis is there is no much significant difference between intelligence level. Please do write a sentence also which I am telling for you. Mu1 equal to mu2 means the group of boys and group of girls have got same level of intelligence. Or you can write H0 is the intelligence level is same for boys and girls. In a brief notation, H0 null hypothesis is mu1 equal to mu2. H1, this is a alternate hypothesis is mu1 not equal to mu2. So first of all, we have to find common standard deviation, which formula is n1 s1 square plus n2 s2 square n1 plus n2 minus 2, which becomes 9.4. And t, how to calculate t, which is testing statistic, x1 bar minus x2 bar, which is difference between the means, and this sigma into 1 by n1 n by n2 root of that. So which we write 74 minus 70 calculated 9.4, 1 by 12, 1 by 10. The calculated value of t becomes 0.994. And what is the degree of freedom? Degree of freedom will be here how many total sample? 12 plus 10, 22. So minus 1 here and minus 1 here. 22 minus 2. For two samples together, instead of n minus 1, here the sample degrees of freedom was 10 minus 1. 10 minus 1, 9 degrees of freedom we took. Here if there are two samples mixed, then this minus 1, this minus 1, totally 12 plus 10 minus 2, 22 minus 2, 20 degrees of freedom for 95% confidence limits. If it is given in the question, please use it. If it is not given, how to find? For 20 degrees of freedom for 95% confidence limits, I am taking you to the table here. For 20 degrees of freedom for 95% confidence limits, for 95% confidence limits for 20 degrees of freedom 2.09. So let us go back to that example, which is for 20 degrees of freedom 2.086, so that this is less than table value. If it is less than table value, hypothesis is accepted. Then there is no significant difference between the intelligence level of group of boys and group of girls. On the other hand, suppose because of the other data, if this would have been suppose 5.6 something like that, then this t calculated will be greater than the t table value. H0 will be rejected. Then we reject the hypothesis. Opposite of the hypothesis we have to write, which is there is significant, instead of no, you should write there is significant difference between the intelligence of boys and girls. I'll go to the next example, very similar example. Two samples of sodium vapor bulbs were tested for length of life and the following results were got. So type 1, N1 size, sample size 8, sample mean 12.1234 hours, 1234 hours with standard deviation of 36 hours. So 1234 plus or minus 36 hours, because exactly 1234 hours any bulb may not, sometimes more, sometimes less, with the deviation of standard deviation of 36 hours. Type 2, again sodium vapor lamps, where second sample has got 7 bulbs. Sample mean is 1036 hours with a standard deviation of 40 hours. Now hypothesis, what you have to test is the difference in the means is significant. Is this mean is significant? Can you tell that both are behaving different, both the samples are behaving different? That is type 1 and type 2 samples are different. We have to tell that type 1 is not superior to type 2. Okay, so that whether type 1 is superior to type 2, you have to tell it's opposite. So null hypothesis is framed to reject the hypothesis. In the mind, you have to frame in such a way that whatever is asked, it's opposite or right. Usually that becomes the null hypothesis. See what is given here. Type 1 is superior to type 2. What I am framing? Type 1 is not superior to type 2. Means both have got same means. Means mu1 of this, mu2 of this. That is population mean of this is same thing as population of mean of this. Becomes our null hypothesis. Alternate hypothesis is always opposite of this. It is a usual customary to write both the hypothesis H0 and H1. Now, usual customary sample mean, sample size, and standard deviation 1, 2, 3, 4 x1 bar. 8 is sample size and standard deviation is S1 36. Similarly, for second also we have written here. Second also, that is then sigma is calculated. Common standard deviation, whenever two samples are given, there is a formula for common standard deviation. So you have to substitute here and there will be 940.7317. That is square root of this. Square root of this you have to find, which is square root of that is 40.7317. It is sigma square actually. Square root of this is 40.7317. When you substitute all these values, x1 bar minus x2 bar, sigma is square root of this, which is 40.7317. Please correct this, which is 40.73. And n1, n2 you have to substitute here. We are going to get 18.14. Now what is degrees of freedom? 8 plus 7 minus 2. If there is only single sample, 8 minus 1 I have written, or 7 minus 1 I have written. Combined sample 8 minus 1, 7 minus 1, 8 plus 7 minus 2, 15 minus 2. What should be that? 13 degrees of freedom. So now, for this 13 degrees of freedom, T statistic, let us find for 13 degrees of freedom, 95% confidence limits. Here it is, T table. For 13 degrees of freedom, 95% confidence, 2.18. If there is a mistake here, let us note down 2.18. 2.18, whether it is written 2.18. Let us see. So we were here. These two. So this should be 2.18 for 13 degrees of freedom. This is wrong. This is 30. Should be 13 degrees of freedom. This is anyway. This is greater than 2.18. It should be made as 2.18. So since the calculated value is greater than 2.18, so I'll just write for you, which is wait a minute. I'll show you what should be written instead of coming back. I'll be showing you what should be written exactly. This should have been, this should be 13. This should be 2.18 according to the actual table. But anyway, this is bigger than this. This is bigger than this. Hence, hypothesis is rejected. Hence, we conclude that type 1 is not superior to type 2. So here we are concluding type 1 is not superior to type 2. But since the hypothesis is rejected, please note that type 1 is superior to type 2. That is, instead of not, please write type 1 is superior to type 2. Once again, I am changing that. Type 1 is superior to type 2. Just small changes. Instead of not, you should write since the hypothesis is rejected, type 1 is superior to type 2. That is regarding the life of the bulb. So now with this, we'll move to the next example. 1 minute. Now with this, we move to the next example. A sample of size 10 and 14 were drawn. Samples of sizes 10 and 14 were drawn from two normal population with standard deviation 3.5 and 5.2. The sample means were 20.3 and 18.6. That means here directly they are giving sample size N1 and N2, standard deviation is 3.5, 5.2, and average is x1 bar, x2 bar. Test whether the means of the two populations are same, whether there is a difference between the samples or not. What is the test? What you have to test whether the means of the two populations are same. Okay. So now, once again, sample of size 10 and 14 were drawn from two normal populations. So from two different populations they are drawing. That doesn't matter. But whether the means are same in spite of drawing it from two different means. Just like you are drawing from one different company and one more different company, two different samples, and trying to infer that whether though they are belong to different companies, samples are behaving same or not. For that, whatever the previous example you have done, very similarly you have to do. Find first common standard deviation by taking n1 s1 square plus n2 s2 square divided by n1 plus n2 minus 2, and t is x1 bar minus x2 bar divided by this quantity 0.86. So what is the degrees of freedom? This plus this 24 minus 2, that is 22 degrees of freedom, which is t calculated is less than that. 22 degrees of freedom gives you 2.0739, and this is less than the table value. Then it is accepted. Both behave same, though they belong to the different populations, samples behave the same. Now see the next example. 11 boys were given a test in mathematics carrying a maximum marks of 25. Out of 25, in the first test, the students scored like this, 11 boys. After giving extra coaching, again one more test was taken, test 2. For this type of conclusion, whether the coaching was important, whether the coaching was effective or not, to test this, instead of test and coaching, mathematics test and coaching, suppose these are patients. Before the treatment, these are the numbers. After the treatment, these are the numbers. Whether the treatment is effective or not, you can conclude. Similarly, for many things, before and after, we can always conclude using this type of approach. Coming back to this example, before the test type 1, before the test 1, after the test type 2, the students were same. Does the result give evidence that the students have benefited by extra coaching? So this helps you to frame the hypothesis. 95% confidence again. Students are not benefited. It's opposite IR finding C. Students are not benefited. Both the data is same. Usually this is the way of forming the null hypothesis. That is difference in marks. The test 1 and test 2 are same. That is what we first find is we find one more new variable, which is difference in the marks as a variable. 23 minus 24 or 24 minus 23, one of them you can only one direction you can take. 2 minus second test minus first test, or first test minus second test. So if I take second test minus first test, 24 minus 23, 19 minus 20 minus 1, 18 minus 21 minus 3, till 17 minus 19 minus 2. So this is bound in x1 x2 bar minus x1 bar. The whole data is bundled in these numbers. Now this becomes our variable x. The mean of this is x bar, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this should be 11. X bar is 1 by 11 plus this. Or if you don't take all this, it should be, if you don't take 0, it will be 10. So now 1. So standard deviation is what? 1 minus 1 whole square minus 1 minus 1 whole square, x minus x bar whole square for all this, x minus x bar whole square. These are all x values. 1 minus 1 whole square, minus 1 minus 1 whole square, minus 3 minus 1 whole square, up to minus 2 minus 1 whole square. Sum of all this divided by 11 is standard deviation square, that is for the sample. Square root of that is 2.13. Now for this new data, which is x2 bar minus x1 bar, that is x bar is 1, s is 2.13. Sorry, we tell that no, there is no difference between the means this difference is 0. That is the hypothesis. There is no difference, but both the tests are same. There is no significant difference of the benefit of the extra coaching. That time mu is 0 means difference of the mean is 0. Or you can easily conclude, easily make a hypothesis that students are not benefited. Now what is the test statistic? X bar minus mu divided by sigma root by root n. 1 minus 0. This is very important. Why you have taken 0? There is no significant difference between the first test and second test. The means are same. So this minus this is 0. That's why it is taken as 0. So x bar is 1. 1 minus 0 divided by 2.13 square root of n. Square root of n is square root of n minus 1. Sorry, this should be n minus 1. 11 minus 1 because 11 students are there. 1.485. So for 10 degrees of freedom, for 95% confidence, T 0.5. For 5% confidence, for 10 degrees of freedom, it is 2.23. This is less than 2.23 or this belongs to this interval. H not accepted, students are not benefited. This is the conclusion. Accepted means students are not benefited. There is no much difference between the marks. So this is also similar. Two horses A and B were tested according to the time in seconds to run a particular race. Horse A and horse B. So that horse A tested, but horse A 1, 2, 3, 4, 5, 6, 7, 8 times tested. Horse B 1, 2, 3, 4, 5, 6 times tested. So here 1, 2, 3, 4, 5, 6, 7. 7 and 6. So N1 becomes 7. How many times tested also becomes can become a sample. So now N1 is 7, N2 is 6. Test whether you can discriminate between the two horses, whether the two horses are different. It is just like the previous example. Whether test 1 and test 2 are different? No, we shall write there is no significant difference or there is no discrimination between the two horses. See, this itself helps you to frame the hypothesis. Is there any difference? No, you should tell first. No, there is no significant difference between the horses. Or you can use this terminology. There is no discrimination between the horses. So let this be x, this be y, and x bar is this sum of all these divided by 7. X bar is 31.3. Sum of all these divided by 6 is y bar, which is y bar. S square is combined statistic x minus x bar whole square, y1 y minus y bar whole square divided by n1 plus n2 minus 2. That is x minus x bar whole square. Sum of all these means what? 28 minus 31.3 whole square plus 30 minus 31.3 whole square plus and so on up to 34 minus 31.3 whole square. Sum of all that. Second sample you take 29 minus 28.2 whole square, 30 minus 28.2 whole square, 29 minus 28.2 whole square. Sum of all that. Whole divided by n1 plus n2 minus 2, 7 plus 6 minus 2. S square you will get it as this, S is this. Now you got x bar minus y bar divided by sigma into this, it will give you some value 2.42. But at 95% confidence for 11 degrees of freedom, why 11? 7 plus 6, 13 minus 2, n1 plus n2 minus 2 degrees of freedom. We get 2.2 as a table value. Calculated value is greater than to table value. Hypothesis accepted. Whatever hypothesis is there is no difference, is opposite of that. Reject means opposite of this. No, you have to remove. There is this difference between the two horses. That is, the conclusion is there is significant discrimination between the two horses. So this is about how to use the small samples. In the next lecture, we'll come with different type of approach. Given the data, if you have fit already some binomial, Poisson distribution or any other curve, whether the or any other proportionate, you can use the samples from botany, you can use sample from zoology, you can use samples from chemistry, or you can use any other sample. Whether already conclusion is whether correct or not, that will be testing by name chi-square distribution. Till that, we take a small break or see you in the next lecture. But try to download Zoom app in your mobile or in your laptops. Make use of these lectures. Please be connected, my dear students. And I'll come back with the third lecture with the last part of this sampling distribution, which is more interesting. Till that, see you. Bye. I'll sign off for time being. Bye.